Okay, now let's discuss two more applications of operational amplifier, that is, it can be used as an integrator and also it can be used as a differentiator. You know what the mathematical operation of integration is, and you know what the mathematical operation of differentiation is. So here we will discuss how an operational amplifier circuit can be used to perform the mathematical operation of integration. That means how the circuit can be used to perform the mathematical integration of the input signal. That means the integrator is a circuit that gives the output voltage which is equal to the integral of the input voltage. If you provide a sinusoidal wave, sine wave input, you will get an output wave of a cosine wave. That usually we cannot distinguish in a CRO, which is a sine and cosine. But if you give a triangle, if you give a square wave input to a integrator, the corresponding integration will be, it produces a triangular wave output. So while doing the practicals, in order to check whether the circuit integrates the given input signal, we will use a square wave input and the corresponding output will be a triangular wave when it is integrated, when the square wave is integrated. Now you know that the output of an integrator is proportional to the area of the input wave over a period of time. The most popular application of an integrator is to produce a ramp output voltage. That means just by giving a square wave input or some stationary voltage or a constant voltage to an integrator, it will produce a ramp output voltage. Ramp means you know that it is a linearly increasing or decreasing voltage. So if you provide a constant output voltage like this, then the output of the constant input voltage like this, the output of the integrator will be a ramp like this. The magnitude will be decreasing or sometimes it will be like increasing. So if you give a square wave, so depending upon, we will have a increasing and a decreasing output voltage, which is called a triangular wave. So anyway, the important application of integrator is it can be used to produce a ramp output voltage. The circuit of an integrator is shown here. Here you can see that it is a conventional op-amp is used here. The op-amp is used in the inverting mode, or the input signal is applied to the inverting terminal of the operational amplifier. The non-inverting terminal of the op-amp is grounded, and the input voltage which is to be integrated is given to the inverting terminal of the op-amp through its input resistance R, and in the feedback circuit we are having a capacitor. That makes this circuit to be used as an integrator. So an integrator circuit actually consisting of a series resistance is input resistance R and feedback capacitor C. So that makes an integrator circuit. Now let's see how this voltage Vi applied in the input is integrated in the output and obtained as V0, or we have to prove that the output voltage is somewhat proportional to the integral of input voltage. This is what we have to show, or what we have to see for using this circuit. The output voltage is the integral of the input voltage. For that, consider the equivalent circuit of this integrator circuit that is given here. The diagram below represents the equivalent circuit of an integrator. Here the non-inverting terminal is grounded. According to the concept of virtual ground, the node A is at a virtual ground. That means the voltage at the node A is 0. So VA is equal to 0 according to the virtual ground concept. Now you can see that the input voltage is applied to a resistance R, so a current I is flowing through it. So here you can see the current I which is flowing through this one, and at the node A there is no current into the operational amplifier because of the infinite input impedance and virtual ground concept. So we will have a current which is flowing through the capacitor or the feedback capacitor, which is taken here as IC. So the two currents flowing through the circuit are the current I flowing through R, which is the same current which is flowing through the capacitance IC. So we can write it as since VA is equal to 0, I will be equal to IC. The current through the resistance R is same as the current through the capacitor. Now the expression for current I will be given by, which is the current through R, so which is according to the basic Ohm's law, the voltage across R divided by the resistance R will give us the current through it. So the voltage across it is the voltage at one terminal is Vi, the input voltage, minus the voltage at the other terminal, that is the node A, that is voltage at the node A divided by R, which is equal to Vi by R. So I am writing the voltage expression here. Voltage across the capacitor is equal to Va minus V0, which is equal to minus V0 because Va is equal to 0. Now the charge on the capacitor Q is given by capacitance into voltage V0, but the current can be written as I is equal to dq by dt. Here I am representing IC, which is equal to d by dt of capacitance into voltage across the capacitor, that is dq by dt into CV. Here V is minus V0, so the actual expression for IC is equal to d by dt of minus CV0. So here it's not Q but it is IC. IC is equal to minus C into dV0 by dt. So replacing, not changing Q, that is it is actually IC. So IC is equal to minus C into dV0 by dt. So using the expression I is equal to IC, that is I is equal to Vi by R, which is equal to minus C into dV0 by dt. dV0 by dt is equal to minus 1 by RC into Vi, which implies to get the output voltage V0 integrate on both sides, you will get V0 is equal to minus 1 by RC into integral VI dt. So the output voltage of this circuit is equal to 1 by RC times the integral of the input voltage. So this circuit acts as an integrator. So remember the circuit of an integrator, the feedback resistance in an inverting amplifier is replaced by a capacitor, then that circuit will act as an integrator. Now comes to the differentiator. Differentiator is a circuit that performs the mathematical differentiation of the input signal. That means if you give a sine wave input, we will get a cosine wave, or if we give a cosine wave input, we will get a minus sine wave output. Or if you give a to understand this one, if you give, for practical purpose, if you give a triangular wave input, the output voltage will be a square wave. So the output of the differentiator is actually proportional to the rate of change of the input signal. The important application is to produce a rectangular output from a ramp input. That is, ramp is actually like a triangular wave, and rectangular is a square wave input. Sorry, square wave output. So usually a differentiator circuit produces a output voltage which is equal to the differential of the input voltage. So the circuit of a differentiator is given here. Here you can see that it is again an inverting amplifier, but the input resistance R is replaced by the capacitor. The feedback, in the feedback circuit we will have a resistance R. So an integrator circuit differentiator circuit is actually a inverting amplifier circuit with input capacitor instead of input resistor, and input capacitor C and a feedback resistance R. So the positions of the resistance and capacitances are interchanged in the differentiator circuit when compared to the integrator circuit, because you know that integration is exact opposite mathematical operation as that of differentiation, or differentiation is an opposite operation of the integration. So here what we have to show is that the output voltage of this differentiator V0 will be proportional to the differential of the input voltage Vi. That is, we have to show that V0 is proportional to dVi by dt. For that, consider the equivalent circuit of this differentiator. Here you can see that this node A is again at a virtual ground, so whatever current is drawn from the battery by the capacitor will continue its journey towards the feedback resistance R. That means we can write this current IC, the current through the capacitor will be equal to the current through the resistance R. The current through the resistance R can be written as IR is equal to VA minus V0 divided by R which is equal to minus V0 by R, where Va is the voltage at one node, at this node of the feedback resistance, and V0 is the voltage at this node of this resistance, feedback resistance. So the voltage across it is Va minus V0, but here Va is equal to 0 due to the virtual ground concept. Now to find IC, we have to write expression for the charge on the capacitor. Charge on the capacitor is capacitance into the voltage across the capacitor C. The voltage across the capacitor is given by Vi minus Va, which is equal to C into Vi, because Vi is equal to 0. Now IC is equal to dq by dt, the rate of change of charge, which is equal to d by dt of C into Vi. Here C is a constant, you can take it outside, and the voltage, input voltage, is a time varying one, so dVi by dt. If input voltage is a constant, then current is equal to 0, the output of the differentiator will be 0, or there is no output for a differentiator if the input voltage is a constant. So now we obtained IC, expression for IC and IR. So if we equate those two equations, you will get minus V0 by R is the IR, which is equal to IC, that is C into dVi by dt. So V0 can be written as minus RC into dVi by dt. So the output voltage of this circuit is equal to minus RC times the differential of the input voltage. So this circuit acts as a differentiator. Now if the input voltage is a constant, then you will get a output voltage is equal to 0. So when we compare the integrator and the differentiator, here by circuit, if you compare the circuits, in the integrator, where we have a feedback circuit, we can have a capacitor, but in the differentiator circuit, the feedback circuit consisting of a resistance R. In the integrator circuit, the input we are having a resistance, but in the differentiator, in the input we are having a capacitor. The integrator, the output voltage will be equal to the 1 by RC times the integral of input voltage, but in the case of differentiator, the output voltage is equal to minus RC times the differential of the input voltage. Now if you give a constant input to the integrator, it will give a ramp output, but if you give a constant input to a differentiator, the output will be equal to 0. There is no output in the case of a differentiator if you give constant input voltage. Now if you give a square wave input to an integrator, it will give a triangular wave output in the integrator. If you give a triangular wave input to a differentiator, it will give a square wave output. So an integrator is usually used to produce ramp output, and differentiator is usually used to produce rectangular output, rectangular or square wave output. So that's all about the integrator and differentiator. That's the end of this chapter, that is the special devices. Thank you.